Now we're going to take a look at what is called continuity. So in calculus, continuity is used to describe functions whose graphs have no breaks. A break in a graph is called a discontinuity. And there are three types of discontinuities that we will look at. The first type of discontinuity is where a graph has a hole. And in that case, that's called a removable discontinuity. And here you can see where the graph is discontinuous. In this example, the graph would be discontinuous at x equals a. The second one is a vertical asymptote. So you can see there's a vertical asymptote at x equals 0. And that would mean that we have a discontinuity at x equals 0. And this one's called an essential discontinuity. And finally, we can have a jump discontinuity. And for us, we will normally see those for piecewise functions. So for the following three examples, we see in order for us to draw this graph, we'd have to lift our pen off the paper. And so that's why we call these discontinuous functions at those particular points. A function f is continuous at x equals a if the following two conditions are met. The first one, the limit at x equals a must exist. And secondly, the limit must equal the value of the function at x equals a. And if it fails condition 1 or condition 2, then we say that f is discontinuous at x equals a. Let's go back and look at the previous three examples and decide which condition does it fail, the first one or the second one. So let's start with our first example, the case where we have a hole in the graph. Well, clearly we see that the limit exists, so the limit as x approaches a of f of x, we see that it exists, and it equals some number. However, f at a does not exist. So this one passes condition 1 but fails condition 2. The limit as x approaches a of f of x does not equal f at a. So therefore this function is discontinuous at x equals a. Second one, we can see it fails the very first condition. The limit as x approaches a, and in this case 0, of f of x, we see that approaches infinity, which means the limit does not exist. And finally, the last one. Again, same as the second one, the limit does not exist. And we can see that by the left and right hand limits. So therefore, this is also discontinuous at x equals a. So let's take a look at our examples. Examine the continuity for each function. So let's look at the first function, x minus 2 squared times x minus 4. This is a polynomial function. So we have a 0 at 2 and a 0 at 4. That's a double root at 2. And since the leading coefficient is positive, our graph looks something like this. Now notice there are no breaks, gaps, or holes in this graph. And therefore, this function is continuous for all x. And this is true for all polynomial functions. So for this example, we don't have to test for any points of discontinuity. Let's go to our second example. X squared minus 4 over x minus 2. Where could there be a problem for this graph? So in this example, we're going to test x equals 2. That is because f of 2 is undefined. Alright, so let's see what happens at x equals 2. So let's go through our first condition. We're going to check the limit as x goes to 2 for this function f of x. So for this one, we're going to factor and see what happens. You see we can cancel out the following factor, and we're left with the limit as x approaches 2 for x plus 2. Using direct substitution, it tells us we have a limit and it's equal to 4. So this does pass the first condition. However, we already know that f at 2 is undefined. So this fails our second condition. Since the limit as x approaches 2 of f of x does not equal f at 2, then this function is discontinuous at x equals 2. So in this scenario where the limit exists and the function is undefined, gives us a graph with a hole in it. So our function is equivalent to x plus 2, so starting here, and then at x equals 2, we know we have a hole, and the limit is approaching 4, so that hole is at 2 and 4. So this is what our function looks like. It looks like the graph of x plus 2 with a hole in the graph. Alright, so next one is a piecewise function. And for this one, we're going to test 2 points, the points where it changes from one function to another. So here we're going to test x equals 0, see what happens, and we're going to test x equals 3. For this one, I'm going to graph and prove that it's continuous or discontinuous. So let's start with the first piece of the graph. It's x plus 1. So x plus 1 starts at 1, and it can equal 0, so we're going to fill in that dot, and it has a slope of 1 over 1. So there is the first piece of that function. The second piece is also a straight line, and at 0, it has a value of 1, but it can't equal that. It has a slope of 3, so that's up 3 and over 1. And when it reaches this point, it also has a hole here. And that hole would be at, if we sub in there, that'd be at 10. And then finally, we have a quadratic function. Again, we're starting at 3. We sub 3 into the equation, we get negative 3. So 1, 2, 3. So somewhere down here, we have a closed dot. It has a vertex at 5 and 1, and this parabola opens downwards. So this one looks something like this. So this is the graph of the piecewise function. Let's go through the test for x equals 0. So first of all, we see the limit as x approaches 0 for this function. We see that it exists and it's equal to 1. We also see that f at 0 is equal to, well, for f at 0, we can only take this function here because it's defined when x is less than or equal to 0. So that's going to be 0 plus 1, which we already know is equal to 1. So this function is continuous at x equals 0. So we can see since the limit exists and since the limit equals the value of the function, and that should say f at 0, then f of x is continuous at x equals 0. So let's test x equals 3 now. Well, this one we can see right away that the limit as x approaches 3 of f of x does not exist. And why doesn't it exist? Well, that's since the limit as x approaches 3 of f of x, so 3 from the left, does not equal the limit as x approaches 3 from the right of f of x. We can see that here. Here's 3 from the left, here's 3 from the right. They do not match up, so the limit does not exist. And since we know that, then f of x is discontinuous at x equals 3. And that's an example of our jump discontinuity. And our last one, 1 over x minus 2. In this one, again, we're going to test x equals 2, since f at 2 is undefined. In this one, I'm just going to do graphically. So we have a vertical asymptote at x equals 2. Our graph looks something like this. And for this last example, we see that the limit as x approaches 2 from the left and from 2 from the right, they don't match. And therefore f of x is discontinuous at x equals 2, since the limit at x equals 2 is undefined. And in that case, that would be our vertical asymptote discontinuity, or what we call an essential discontinuity. So try the following questions from your book, and then I've left you a question. Determine the values of a and b that make this function, f here, continuous everywhere. And then you can verify your result using graphing technology. So again, this is 3 pieces for our piecewise function, And I want to know what values of A and B will make sure that all three pieces join up at x equals 2 and at x equals 3. If you have any questions, please let me know.